All right. I hope you are ready for fun and excitement today. And I'm not kidding. I'm not kidding because I'll tell you, this is actually a skill, this thing, Hess's Law here. This is a skill that I have been told on more than one occasion is actually kind of fun. Um, in fact, I remember when I first learned this, and keep in mind when I say things like that, it was when I first had to teach AP chemistry when I was at Clay High School, and I retaught everything to myself. And in a sense, I actually retaught all of chemistry to myself because I didn't know that much. And I remember when I was first learning or relearning how to do this, I thought it was actually really fun. And I know that's such a geeky thing to say, but it's like a puzzle. Hess's law is really a very cool thing. As long as you know the steps to take and how to solve for the things that we're going to be doing today, you're really going to find it quite easy because it's puzzle like and it kind of has a little bit of algebra to it. It's really kind of neat, and it's just kind of a fun little thing that we can do with these thermochemical equations. So if I haven't just completely lost you with my geekiness, then we'll continue. Okay, so we are actually moving back to the Zoom doll book at this point. So it's section 6.3 in your Zoom doll book. So go ahead and have it open to that section. We will be referring to page 258 shortly. So we'll be getting to that. Okay, so in the very last presentation that we did at the very end manipulation of thermochemical equations. So do you remember the two rules? There was a rule about if we multiply or divide a reaction by a factor, that we have to do something then to the delta H also. Remember, it was basically the same thing. So if we multiply by 2, the whole reaction, then we have to multiply by 2 also that enthalpy value. And the second one was that we had to, if we had to reverse a reaction, then we would change the sign, reverse the sign of our delta H value. So if it was an endothermic reaction, it would become an exothermic reaction. So those are the two rules that we're going to be working with today as we do something called Hess's Law. So what Hess's law deals with as an introduction, we will learn how to use delta H values from a set of reactions. Notice at this point, we've actually only dealt with one reaction at a time. And so now you're going to be given sets of reactions to determine this overall kind of one reaction we care about. But the set is where you understand what we talked about earlier, about how it doesn't really matter if you go to Defiance directly by 24 or if you take the back roads. The point is you get there. And that's what's called a state function. So the reason why you can take a set of reactions and apply it to sort of an overall reaction is because H is a state function, or enthalpy is a state function. Depends on the initial and the final state, but the intermediate steps, the roads you take to get there, really doesn't matter. It's about your reactants that you start with. Ooh, can you hear the car in the background? It's about the reactants that you start with and the products that you end with, and that's it. So if the initial reactants and final products for the set are the same as the final single reaction, then it's all going to work out. And at this moment, what I'm saying may seem a little bit cryptic, like you're not 100% sure what the heck I'm talking about. And if that's the case, I highly suggest just stick with me and go back and look at this at the end, and I think you'll completely understand what we're saying. Okay, so this is actually completely called Hess's law of heat summation. And hopefully you'll see the word summation and realize that that essentially means we're adding things together. So we're going to be adding reactions together. The definition is this. For a chemical reaction that happens as the sum of two or more steps, the enthalpy change of the overall reaction equals the sum of the enthalpies of the individual steps. Okay, so it's almost like saying, well, if I lived 10 years and then I lived another 25 years, how old am I right now? That would say I'm 35, which is a true statement right now, today. I know, I'm old, right? Okay, moving on. So it makes sense. You just add them all together. Hess's law is helpful because it allows us to determine the delta H value for a reaction that may be difficult or dangerous to do by direct experimentation. So keep in mind, again, there's a lot of chemical reactions out there that we don't really want to do if we don't have to. like honestly, blowing up large amounts of gasoline. I mean, that's not something that I would want to do in our chemistry lab at school. But if I really needed the enthalpy value for that reaction, I could actually do more safe reactions, do multiple reactions that are more safe, but they all end up factoring into that final equation that I actually cared about. It would actually be possible. So here's what we're starting to mean. When we talk about using Hess's law, you're going to get something that looks like this. So notice that you have here two reactions at the top. You have a sulfur and oxygen combining to make sulfur dioxide and the enthalpy value for that. You've got sulfur trioxide, which is actually being degraded into sulfur dioxide and oxygen gas, sorry, and then the enthalpy value for that. And then they say, predict the delta H for this reaction. So you should see the same components. You'll notice that there's sulfur in there, that there's oxygen in there, and that there is sulfur trioxide, and then we don't know what the enthalpy is. So this is what the problem would look like. You can see the set of reactions at the top, but that set of reactions can be done in such a way that it will equal the final reaction that's listed at the bottom. Okay, and here's how we're going to do it. So here's the information that I just gave you at the top. It's written a slightly different way, more like a mathematical problem where the big big horizontal line represents, your equals line. So the two equations above need to equal the equation below. And we are going to have to do some work to make that happen. So the first thing that you'll always want to do as you begin to work with Hess's law and the manipulation of thermochemical equations is to note where each substance is in the final equation and determine if reactions must be reversed. So what do I mean by that? Well, let's see. If you look at the final equation, this is what we're trying to match. Do you see how the sulfur trioxide is a product? Yet the sulfur trioxide listed in this equation is a reactant, and that doesn't match. So that's what we're saying. We got to make it all match. So if sulfur trioxide is a final product, we need to reverse equation number 2. And if we reverse equation number 2, think about what we talked about in the last presentation. You must also reverse the sign of your delta H. So we now have an adjustment, and it looks like this. So note what I did. Note that equation 2 was in fact reversed, and then that positive 198 became a negative 198. Okay? So I flipped it. Now it matches. Okay? Follow? Good? Okay, next. So here's my adjustment. This is the new stuff that we've just created. And now we will do our next step. We want to note the coefficients in the final equation. So again, first step was note products and reactants, and the second one is now coefficients. Will any of the reactions need to be multiplied by a factor in order to produce the coefficients that we see in the final equation? Okay, so the thing I'll draw your attention to is this. Do you see how there's 2 sulfurs? But here, well, there's just one little lonely sulfur. Well, that's a problem. And by the way, do you notice here? 2SO3, 2SO3. There's a match. So that's telling me that my second equation is fine, but my first equation has an issue because it's a 1 versus a 2. So 2 is before the sulfur solid in the final equation, so I need to multiply equation 1 by a factor of 2. And what effect will that have on the enthalpy? Hopefully you said that I'll also be multiplying that by 2. So here is now the new adjustment that I have. So you can see I don't just multiply the sulfur by 2, but that 2 is carried across the whole equation. Basically, I'm just doubling the equation, like I'm doubling the batch of cupcakes I wanted to make. And I get more cupcakes. I get more energy out. So I now have my adjustments. And at this point, we need to decide if we're ready to be done. Basically, have we gotten it to the point where it matches now? And so this is the question. Are we ready to cancel? This is where the algebra part kind of comes in a little bit, because what I have you note is there is sulfur solid, there's oxygen gas, and there's sulfur trioxide. What chemical does not exist in the final equation? Hopefully you were pointing out sulfur dioxide. But in fact, look at this. Do you see on the product side here, it's 2SO2? And on the reactant side here, it's 2SO2. And just like an equal sign, that arrow represents an equal sign. And so I am actually able to cancel out the 2SO2. And I'm actually then able to verify that everything is the way it is. So do you see, or the way it's supposed to be, that is. So do you see 2S solid, 2S solid. Here's 2O2, and there's 1O2 for a total of 3O2. And then 2SO3 and 2SO3. Okay, so it all matches. And at the point when it all matches, you're now ready to do the math. And if you go back to the definition, it said that we needed to make sure that the steps, that the reactant or the reaction steps matched a final equation, and then we would be able to take the sum of the enthalpies to get our final answer. So you can see that you just add your negative 594 and your negative 198, and then you get to negative 792 kilojoules per mole reaction. Which is something I haven't said yet in this one. So remember we talked about per mole reaction. It usually gets shortened to this, kilojoules per mole. So that means per mole reaction, which means that if you start messing with coefficients or amounts, or, I don't have 2 moles of sulfur solid, I only have 10 grams, then we would have to do adjustments stoichiometrically to fix that all up. So that's the basics of it. It really just comes down, like I said, to kind of like fitting a puzzle together. So you have to flip this thing. It reminds me of like a Rubik's Cube. Flip this thing, multiply by this thing, and then everything cancels and you're back to square one. So what we'll go ahead and do then is move on to a slightly more difficult reaction. Oh, I'm sorry, final answer. So here in yellow is just the way that the final answer would be treated. You have the complete equation as it was listed at the beginning of the problem, and then your delta H value final. So this is your final thermochemical equation and your final answer. Good. Okay, so we're going to move on to a new example that now has 4 reactions. So in the previous example, we had 3 total reactions, 2 steps, and then the final. Here we've got 3 steps and a final, which is very exciting. So we want to find the delta H value, or the enthalpy of reaction value, for W solid. Anybody know what W is? Anybody out there say tungsten? Good, good. By the way, tungsten is the very thin filament in regular old incandescent light bulbs. And so you heat that tungsten filament up and it glows bright and you got a light bulb. Ta-da. So tungsten solid plus carbon graphite will yield, tungsten carbide, which is the solid listed there. So take a look at this. Remember your steps. We generally want to look for things we may need to reverse reactions first, and then we want to look at coefficients. And then we want to start to do some canceling. So I'll leave this up to you. If you want to pause the video for a second and maybe see if you can work it out, go for it. If not, just let the video keep rolling and I'll explain it as we go. Okay, so the first thing that I'm going to do here is I'm actually going to reverse equation 3. The reason why I'm reversing equation 3, hopefully you can find the reason. Yeah, it happens to be the 2WC. I need that to be on the product side. So I need to reverse that reaction as well as the sign of delta H. And that will also, as sort of a nice helpful thing, this WO3 and the CO2, these do not appear in the final equation note. And if I switch the equation, that is also going to eventually allow me to cancel out the tungsten trioxide and the carbon dioxide. So that's just kind of like an extra added bonus, yippee. And then the other thing that I'm going to need to do to make sure that everything matches is multiply equation 2 by a factor of 2. The reason being, can anybody figure that out? Why would I need to multiply reaction 2 by 2? Well, what it's going to come down to is the carbon dioxide. I have to be able to cancel out the carbon dioxide. Notice that the carbon dioxide, as listed here, I have 2 CO2 and there's only 1 CO2. So if I switch reaction 3 and then multiply reaction 2 by 2, I now have the 2 CO2 on the reactant side, and now I would have 2 CO2 on the product side. So you're kind of like looking through the whole thing. Okay, so once we do those steps, please note the changes. Note that my reaction 2, I multiplied the enthalpy by 2, and notice that in my reaction 3, I have reversed the sign of my enthalpy plus the whole reaction itself. And now you can also see that I've canceled some things. So we already talked about how the tungsten trioxide would cancel, and here the carbon dioxide cancels. But my question for you is, anything else? Anything else? Hopefully what you're looking for is something that's in those steps that's not in the final equation. And I hope you're seeing oxygen gas. Oxygen gas cannot be there, so we've got to cancel it out. So take a look at this. Do you see how we had 3 and 2 on the reactant side and then 5 on the product side? Well, we can actually cancel it all because it's just a summation type of a thing here, so works pretty good. All right, so we're left with 2 of the tungsten, 2 moles of tungsten, 2 moles of graphite, and then 2 moles of the tungsten carbide. And the question still is, what is the delta H value? Now, I have to ask. Oh, and by the way, that would be the delta H value if I add them all together, right? Okay, so you can pause if you want to and do the math and verify that I get the negative 76. But is there a problem? Think about it. Think about it. Look closely. Is there a problem? Okay, what I hope you notice is that in the original equation, they didn't have any coefficients. It was just ones, ones, ones. And here we got two, two, twos. So yeah, that's a problem. I have to reduce. I didn't actually produce the equation that they wanted me to. And again, this is an extensive property. So if I have double of everything, I'm going to be producing double the heat. So in this case, I'm essentially wanting to divide the equation by 2. And then I will treat delta H the same by dividing it also by 2. So this would be my final answer. All right, so we've done a couple of examples together, and then I would like you to take a moment and try a sample. Okay, so hopefully your answer would have had you do the following steps. Reverse equation B, and then you have your new delta H value, which is now positive instead of negative. Hopefully you've multiplied equation C by 3 and then produced your new delta H of negative 858. Multiplied equation D by 3 and then adjusted your delta H appropriately. Hopefully you then canceled, and hopefully your final answer is positive 36 kilojoules per mole. Hold on, Travis. And I gotta go. Good thing we're at the end, right? All right. Write your questions down, and we'll see you later. Bye-bye.